people in Zoom land is listening to me or is hearing me. So it's a great pleasure to have Tjonnie here, who I know since 5 or 4 years ago. So Tjonnie is an associate professor both at the Chinese University of Hong Kong and Leuven. Tjonnie obtained his PhD at NICAF, if I recall correctly, in 2013. And then he moved to Caltech to the LIGO laboratory with a Rubicon fellowship, to then move in 2015 to the Chinese University of Hong Kong as a research assistant professor, where then he became assistant professor and now associate professor. So he's also a member of the LIGO collaboration. He's been chairing the group that works on testing general relativity with gravitational waves for a few years now. And he's also former awardee or holder of many prizes and prestigious fellowships, like the GWIC Thesis Prize for the best thesis in gravitational waves, or the Curvature Innovation Award, which is a kind of Hong Kong starting grantee. Do you want to say it like that? Sure. So, as I said, Tjonnie's work focuses mainly on testing general relativity with gravitational waves and searching for signatures of gravitational lensing. But today he's going to tell us about numerical relativity code for simulating astrophysical systems that they've been developing in Hong Kong. So the floor is yours, and thanks for coming.
Thank you. And thank you very much for those who are here and those who are on Zoom. I hope I'm audible. If not, please do let me know. I saw that there was something written in the chat.
Yeah, they said they can hear you well.
Perfect. Okay. Yeah, it's a great pleasure to be here. I really enjoy this lovely place. And now also get a chance to share with you some of the work that I've done. Before I start, I will make everyone regret not coming in person, because I did bring Dutch snacks, cookies. They may not look impressive, but trust me, this is more addictive than cocaine. I will hand this around. Oh, you can just take one and just pass it on. There was plenty for everyone, but since, you know, some of you are not here, you can even take two if you want. The other thing I want to say before I get started as well is that this talk, even though I'm giving it, I really want to give a special mention to the 3 students who actually done the work. Okay, so I've listed them here. And of course, this doesn't work anymore.
Oh, yeah.
Yeah. So these are the 3 students, Patrick, Alan, and Harry. And these are the 3 who've really done all the heavy lifting. I will be presenting it. I would say don't ask me questions, because you know I will only redirect the questions to them, so to speak. But still, today I want to show you something that is a little bit outside the usual thing that we do in the group, but it is something that we've been working on quite a lot in the last few years, and that is probing extreme phenomena using multidimensional, general-relativistic, electro-magneto-hydrodynamic simulations. So it's pretty much all of the fundamental forces you can conjure up, and we're trying to put all of that into the simulation to understand astrophysical phenomena.
No, I should do the. No.
Not going forward. One second. Let me try this. No, press forward. No.
Yeah, otherwise you can use.
Yeah, I'll just use
the arrows.
yeah. That's also not working.
Maybe that's okay.
Let me try that. Yeah. Okay. So again, just before I start, the premise may seem quite simple, right? We've got Einstein's field equation, we've got conservation of rest mass, conservation of energy momentum, some equation of state of the matter you're considering. Towards the end, I'm even going to show you how to even couple in Maxwell's equations for the electromagnetism part. And then we have, you know, typically also worry about the stress energy tensor. So pretty much just sticking all of this stuff in and let the system run. That's the premise of the entire talk. Okay. Now, of course, I want to give a little bit more detail how we actually do this, and then show some application of the work that this code can now do. So again, just to zoom in a little bit more on detail. So in terms of physics, what we're aiming to implement is, as I said before, a general-relativistic electro-magneto-hydrodynamics code. So this includes ideal and resistive GR-MHD. And again, I will show more, but it shows divergenceless handling. It was originally created with a constrained evolution scheme for the Einstein field equation part, but that's something that I will also show that we're actually expanding to the full treatment of GR. And in terms of the numerics, adaptive mesh grid, parallelized, multidimensional in 1, 2, and 3 dimensions, and in curvilinear geometries. So that's really just the setting. So let's talk a little bit about the formulation of the Einstein field equations first. So what is usually done is the so-called 3+1 decomposition, or ADM framework, where we're aiming to solve Einstein field equation here. And what you can do is, if this is your spatial foliage, then you can decompose this in a 3+1. So you've got the spatial part, you got the time part, and then you try to evolve the spatial part throughout the time part. And then you can write the metric in this form here, where this gamma here is the spatial metric, and the other ones are then functions of vectors. You can see here alpha, beta, and so on. So the starting point is to look at the extrinsic curvature. So this is how your 3-dimensional hypersurface is curved, and you can write this in this particular form. Again, I'm going to show a little bit of maths just for completeness. The point of the talk is not necessarily to go through all the maths, but once you have defined this extrinsic curvature, you can then obtain here in equation 5, you can obtain the extrinsic curvature evolution equation. Okay, so that's again, when you have this 3+1, how do you evolve this notion of this extrinsic curvature throughout time? Okay, so we can do the same thing for the energy momentum tensor. We also decompose it in the same 3+1 ADM formalism, and we end up with 2 constraint equations. And these are the equations that you have to satisfy at every step of the time. So we have one way to evolve things, and then we have 2 constraint equations that we have to satisfy. And then how you exactly do this, that is the subject of many different codes. Different formalisms end up taking slightly different approaches of how to solve this. So again, just to reiterate, so we've got the momentum constraint and the Hamiltonian constraint that came from the energy momentum tensor. We've got the extrinsic curvature evolution that we saw before here. And then the final step, final ingredient here is how to evolve this 3 metric, the spatial metric, that I actually decomposed from the beginning. So this is pretty much the context. If you just talk about the Einstein or the gravity sector, this is how you do it. And exactly how you do this, where you give your weights towards more the evolution side or the constraint side, that determines different formalisms, different codes like BSSN and so on. Okay, so one thing that we started off with is, for this code, is to use the conformally flat assumption. So the way we evolve this 3-dimensional metric, so here in equation 15 on below, is to simply say, okay, we assume that there's an independent flat background metric, Fij, and we have a conformal factor, so that we can now write the 3 metric in this form. And then if you do so, and once you do so, you can rewrite your entire set of equations, but the gist remains the same, right? We have the evolution equations and we have the constraint equations. And in this case, if you do the conformal flat formalism, you end up with the evolution equation to look like equation 19 and 20. Okay, again, the actual mathematical details are not the crux of the story, but I'm showing them for completeness here. Okay, the constraints, again, you can do the same thing, right? Once you have made the assumption that you've got this conformally flat 3 metric, you can also transform the Hamiltonian and the momentum constraints into equation 21 and 22. And then finally, you need to impose a gauge condition. And in our case, I don't want to go into too many of it. Yeah, it's here for 2 minutes. Okay, so moving on, we can then talk a little bit about the relativistic hydrodynamical equations. And in this case, what we do is, you start off with the assumption of a perfect fluid. So you've got T mu nu equals rho, H u, and then PG, G mu nu. So these are the usual kind of meaning of the symbols. So you've got the rest mass, forward velocity, pressure, enthalpy, and internal energy. And then again, you can pick out a specific class of observers, the 3 velocity for the Eulerian observers. And then you can write the formulas. We can do this decomposition again into various aspects. So we can then think about the continuity equation for the rest mass density, the energy momentum conservation, and then you can write the entire set of conservation laws in this form, where the Q, F, and S are defined here. Okay. Again, I apologize. This is something that is necessary to show the full set of equations. And so this is really where how we treat the hydrodynamics part of this story. Okay, one extra thing I wanted to also highlight is that we actually, in our code, we use the so-called reference metric formulation, where when you consider systems with approximate symmetries, so this could either be spherical or rotational symmetries, then it actually makes sense, and I think everyone has seen this for many times, it makes sense to use spherical or cylindrical coordinates. And so what you can do is then actually do your conformal decomposition of your spatial metric that we've seen before, but also do that in these different coordinate systems. And that way you actually end up saving a lot of problems and also singularities that you end up avoiding. So in our case, even our metric, our background metric, we actually decompose it into the coordinate systems that we are aiming for as well. Okay, so you end up with the hydrodynamical equations that look like this one here. Okay, so the reference metric formulation, and the reason why we picked this out is that it actually ends up fitting more naturally with the code that we have. So in particular, I'll show later, we use adaptive mesh grids, and so in curvilinear coordinates. And so having the reference metric to be defined in the same coordinate system will actually end up saving us a lot of problems, because you can end up replacing all the spatial derivatives in the flux and source terms. You can actually factor out terms that you can end up canceling in terms of numerical errors also, and then computational cost and so on. These are all improvements and the reason why we use this reference metric formulation. Okay, there's a lot of detail in the numerics part, which I will completely not go into, because I think it's more fun to actually look at some of the physics that go behind it. But just to highlight what we do, so as I said before, we use MPI for parallelization. We have block-based adaptive mesh grid refinement. The code is written in multi-dimensions, so we can use Cartesian, spherical, cylindrical coordinates. There are different divergence cleaning methods for the magneto-hydrodynamics, which I'll talk about more later. And then initially, the code was written with this conformally flat approximation in mind. Again, towards the end, I'll show you some of the work that we've been doing to further extend this. Okay, and then again, other, and this is even more algorithm side, how we treat finite volume methods, Riemann solvers, RK solvers, also all sorts of this. Okay, so the first thing I wanted to talk about in terms of the application is in our study to understand neutron star seismology. or astroseismology. So this is the study of how a neutron star oscillates. Because now we have a code which is GR-HD, right? So it couples the hydrodynamics with the gravity sector, and so we are able to simulate things like neutron stars. And so, just a brief kind of introduction on neutron star seismology or astroseismology. So, all of these major gravitational wave sources, consider to a certain extent, some neutron stars, right? We can look at hypermassive neutron stars as remnants of a binary coalescence, but also for proto-neutron stars in core collapse supernovae. Now, neutron stars have a rich spectrum, right, of normal oscillation modes. So you can think about in terms of F modes, G modes, R modes, W modes, and all these things that we even use to characterize the Earth with. We can also use that to characterize the oscillation properties of neutron stars. And so what we end up are specific damping times and mode frequencies that end up being very sensitive to the equation of state of matter that we've considered, to spin, magnetic field configurations, and so on. So when you have access to these damping times and these oscillation frequencies, the hope is that we end up learning more about the properties of the neutron star itself. Now, one thing that is kind of been under intense study in recent years are these so-called universal relationships. So these are relationships that are universal in the sense that they don't sensitively depend on the equation of state. So these could be, for example, when we look at the gravitational mass, the radius, tidal deformability, and spin. There have been, on different aspects and different levels, there are these universal relationships that relate these things with each other in a way that is insensitive, or at least not very sensitive to the equation of state. And that's something that we will also explore, right? In this work, we will also explore the nature of these universal relationships. Now, once you have these, and once you have the understanding, of course, the ultimate goal to go to is the understanding of the ultra dense matter, so the equation of state, which is something that at least is challenging to calculate from a theoretical basis. So the measurement may give us some insight there as well. And then lastly, other effects could also be present: quark matter, superfluidity, superconductivity, phase transitions, and all these things are also postulated for neutron stars or similar compact objects. Okay, so now when we think about it in terms of a binary, so when we think about gravitational waves emitted by two neutron stars that orbit each other and end up coalescing, then you actually in that process also excite the oscillation modes of the neutron stars themselves, right? Because there's, to a certain extent, there is some influence of one body with the other body. And so as it goes through its orbit, you end up having the possibility of exciting these oscillation modes. Now, in the early in-spiral, so what I mean by in-spiral is when the two objects are still far apart, they orbit each other in a quasi-circular way, and they emit fairly regular gravitational waves. So here we look at adiabatic tidal excitation, so that's the way the two things are locked, right? It's tidally interacting. And that ends up also being able to excite some of these neutron star modes. So that's actually an interesting avenue for us to look into, how do the gravitational waves that we may see link to the internal structure of the neutron star itself. Now, if you go even further, the expectation is that then at some point, some of the dynamical tides actually end up exciting the F mode specifically during the late in-spiral phase. So when the tidal effects are stronger, then this whole concept of dynamical tides end up exciting the neutron star modes. Now, these are the two in-spiral sites and how this neutron star oscillation fits in. We can also look at the so-called post-merger. And so once the two objects have collided, they typically form either a stable or an unstable hypermassive neutron star phase. So this is where you have all of this matter still in a particular oscillation or a particular state, which oscillates, that then, if it's not stable, collapses into a black hole, or, if you're lucky or if the conditions are right, it remains to be a heavier neutron star. And so even after the merger, we expect to see the signatures of these oscillation modes that are there in the neutron star. So there are different ways, different aspects, which all excite some parts of these neutron star modes. Okay, so this is just an example where what I'm showing is the frequency on the x-axis, and then this is the gravitational wave signal. And in this case, this is the hypermassive neutron star, so after the merger, and you can see that the formation of these characteristic peaks, right? So this is so-called F2 peak, which is something that we observe from numerical simulations, but the question remains, okay, what exactly are these modes that we see? And here you can see more or less the same thing, but with a more modal decomposition. So this is for the hypermassive neutron star. Now, for the in-spiral part, of course, I mentioned also that you can get these dynamical tides oscillating the neutron star modes as well. This was a recent paper in Nature Astronomy, where given the measurement of the tidal deformability of BNS event that we've had, that we've seen before, they can put additional constraints on the equation of state and on the measurement or the existence of this so-called F2 oscillation mode. Okay, so that's pretty much the the context, and so let's go to what we knew before we conducted this study. And so we know that the quadrupolar L2 fundamental fluid mode has the strongest tidal coupling during the late spiral. Right, this is some of the dynamical tides work, where it was identified that this L equals 2 mode has a strong tidal coupling towards the end of the spiral. And so the dynamical tide actually couples and excites this 2F mode, which are then the dominant effects, right? When the tidal forcing frequency approaches the frequency of the 2F mode. So we call this F2F. So what happens indeed is that when the conditions, when the forcing frequency kind of approaches, so when the orbital frequency approaches this this fluid mode, you can see the ramp up, and so you get extra phase shift in your gravitational wave signal. Okay, the other things that we know is that there is a universal relationship, and I'll show that in a moment, between the mass weighted. So this is you weigh that with the actual mass of the object. So there's a universal relationship between the F, the frequency of this 2F mode, so the quadrupolar L2 fundamental mode, and the so-called tidal deformability of the star itself. So that's the first universal relationship. And the second one is that the frequency at the maximum amplitude of the gravitational wave, which we refer to as Fmax, also has a universal relationship with this kappa T2, with this tidal deformability. So these are two universal relationships that have been observed using more theoretical studies, but also using simulated settings. And the goal for us, at least in doing this study, is actually end up trying to find a connection between these two universal relationships. So why is the fundamental frequency of a neutron star, which is tightly related to the tidal deformability, why is that also related to the maximum amplitude frequency of a binary neutron star? Right? From the onset, you may think, well, okay, the two may not be necessarily related, even though, when you think about things like dynamical tides, you can understand that there may be some coupling between those two processes. Okay, so what we did is we simulated isolated rotating and non-rotating neutron stars using our code Gmunu in two-dimensional spherical polar, and using the Valencia formulation I just showed with the reference metric, and then other detail as well. Now, the thing that I want to point your attention to is that the initial data was obtained from another open source code XNS, which basically simulates the initial data for this neutron star, and then that is actually put into our code Gmunu to be evolved further and observed. Okay, I think
There's a Leuven.
yeah, okay. That works. Okay, sorry about that.
Try now.
Okay, so the mass range that we are observing or that we're simulating ranges from 1.2 to 1.4. So all well within kind of the observational limits that we have for neutron stars. We have 4 different equations of state, 5, I think, 5. So from soft to stiff, these are the equations of states that we're considering. And importantly, we also consider different velocities, different angular velocities. So non-rotating to, two rotating or 2 sets of rotating neutron stars. And then we use, at a single point, we extract from the Fourier transform the non-radial velocity component at particular angles to obtain the F mode.
That's weird. Use also the mode.
Okay. So that's how we got the the 2 F modes, right, through simulation. Now, in terms of Fmax, right, because that was the other universal relationship we wanted to approach, the definition is a little bit less straightforward. But if you consider here on the top, this is a typical gravitational wave signal as a function of time. And you can see the in spiral here in the beginning part here. And then as it goes along, you get this runaway process. And at some point you can identify, it's a little bit heuristic, you can identify what's the peak amplitude. And at that point, you can also look at the equivalent Fourier transform and actually find, okay, what is the frequency of the maximum amplitude? Okay, so that's how in the numerical simulations of PNS.
You're looking at the frequency of time is equal to 0, right? Not the maximum.
Actually, no, this is the thing that we did.
Okay.
Yeah.
The maximum.
Yeah, so it's the amplitude. Yeah, it's yeah.
Well, that's not what you said. You said the frequency of maximum amplitude.
Right, but amplitude in
No, I mean,
its frequency of maximum amplitude, okay, in the frequency domain, the peak in the frequency domain.
okay, so you're not showing the Fourier transform.
Okay, so this is a frequency time plot.
Sure.
Actually, no, okay, no, I think you're right. 1 second, let me think. No, you're right. No, it is that at 0, you identify the peak, and you set that at 0, and you take this frequency here.
Okay.
Not this one. No, this is at 7,000
Okay,
hertz.
so this is something like the end. Well, if you think of you asked the question, what's the end of the spiral?
Yeah.
After that time, I guess, certainly no longer think of it.
So actually, this is actually something that we will come to later on in the interpretation side. But you're right. Even at this peak amplitude, the question is whether there's still 2 identifiable objects available for you to consider the orbital frequency and things is a little bit not that clearly defined, and that's actually one of the issues that we will hit on after later in the interpretation stage. But you're right. No, this is the point that we end up taking. Okay, so for that, so for the BNS simulation, we did not do our own simulations. So what we did is we looked at published material. So extracting these Fmax data for BNS simulations. And so from our side, we just made sure we matched the equation of state and the masses of these systems so that we had the equivalent for these BNS simulations, we have the equivalent of the isolated neutron star simulations. Okay, and again, the average masses for these binaries are exactly in the range that we ended up simulating. And so what we end up doing is to compare Fmax and the frequency of the fundamental mode across all the 5 equations of state as a function of mass. So this is the plot. Oh, okay, something went. Okay, that's fine. Okay, so this is the exact comparison. So it's a little bit busy. So let me try to explain in detail. So on the x-axis, you've got the mass. On the y-axis, you've got the frequency. And there are 2 types of frequencies plotted. So one you can see as kind of bands with 3 lines. Those are the simulations that we did. So these are the isolated neutron stars, and these are the frequencies of these 2 F modes. In the stars, you see, are the Fmax frequencies that we extracted from published data. And so even if you now look at the stars, so let's not focus on the squares yet, you can see that the comparison is fairly close. The Fmax all falls within the bands of the simulated isolated neutron star results. Now the bands are constructed by looking at non-rotating all the way to the fastest rotating ones that we have. So those are the 3 lines that you see. So depending on the exact spin, the rotation of the star, the results of Fmax lie very close to the simulated results of the fundamental modes. Okay, and so here in the bottom, you can actually see the percentage difference between the closest lying line of these results. And you can see they're pretty much at, at a few percent level.
So these are the frequencies at one point for each mass?
Yes, so for every mass, this is the frequency either of the fundamental mode.
At a fixed, at what time? Frequency vary at the time, right?
No, that's what it was.
Yeah, that's for the binary.
So, okay, for the
fundamental mode, it's simply the natural oscillation frequency of the neutron star itself, right? So if you think about the black holes, it's the quasi-normal modes from the black hole. Now, of course, the definition is not as straightforward as for the quasi-normal modes, but yes, you can do some Fourier decomposition of your velocity spectrum to get the oscillation mode of the fundamental mode. But that is a fixed time thing. What isn't a fixed time thing, and this is what we kind of we're looking at before, is that Fmax, so the maximum frequency of maximum amplitude, that is a function of time. But here we calibrated at time equals 0, which we set to be the maximum of the collision or the maximum amplitude. Okay, so you can see that they're remarkably close, right? That's just a few percent difference, which again, you may or may not expect, but this is an actual kind of measured result. Now, the squares that I mentioned before are actually for unequal mass binaries. So we actually ended up simulating, extracting from the literature also the unequal mass binaries. And there you can see a much bigger difference. And we'll kind of get to the interpretation of this later.
So for the binding neutron star case, what is the mass of how you are calculating the mass, total mass of the both, or
Average.
average of the?
Yeah, average of the two. So we ended up, kind of limiting the average mass to 1.2.
So your one single neutron star has 1.2 mass, and then the average of the other binary is actually what you are comparing.
Exactly, yeah. Now that's where you're catching on to the point, and that's why the unequal mass binaries end up not matching as well with the results. And that's mainly because then you have to wonder, okay, where on this plane am I when there's unequal mass binaries? There are other effects like tidal disruption and stuff that we need to consider. I'll talk about them in a little bit later. But for the equal mass binary, there is a natural average, or it's just the two. Basically.
All known spinning cases.
So for the these are spinning.
Okay.
So the band that you see.
And even for spins, you do the same thing, like average, like how your neutrons are single and the binary, how they match in spin.
Yes, we simply took the average of the masses itself.
And how do you then check when you get the initial data?
Yeah.
How do you match the spins? Like,
Sorry, so we don't match the spins.
okay.
So for the Fmax, because the problem is, during the simulation, you actually don't know, the spin is not something that is stable or necessarily, well defined. And so the thing that we do have control over is kind of our initial profile of rotation of the neutron star. So that's where the band here comes in. But for the Fmax, and that's why we simulated a range of spins, and that's because we don't know by the time of merger what the spins are of the individual neutron stars. So we took this band so that we were kind of comparing it, hopefully to the right thing. Okay, so just some values here again, just to interpret this delta. But in general, what you see is that there's a better match, so better correspondence between Fmax and the fundamental frequency for the stiffer the equation is stated. Whereas the softer ones indeed have a larger delta. But just bear in mind this is limited by the spin values. So we only simulated 3 spin values. Perhaps if we even go higher up in spin, we could get these values to match better. But again, that's the big problem with these comparisons. Well, it's not a problem with comparisons, but we don't know exactly what the spins are at Fmax. So it's something we can't keep track of. So this is something that we don't necessarily look at very carefully. But still, the main conclusion here is that Fmax is pretty much similar to the fundamental frequency of the neutron star. Okay, and that's really the surprising result. I wouldn't, it depends who you ask whether it's surprising or not, but it's one of these results that we are now empirically observing. Okay, now again, when you go to unequal mass binaries, all of this blows up. This is something that, again, I was saying, the concept of kind of what average mass do you take, but also tidal disruption effects like that are making the problem much less comparable. And so that's why the mass ratio. So once the mass ratio goes up, the deviations go up. It's actually fairly well expected. But actually later on, I will discuss this as well. It may actually be something that we can turn around and say, if you can measure the Fmax and the fundamental frequency separately, then you may have a gauge for the mass ratio of the system. Okay, so now let's put this into the context of these universal relationships. And this is just an example from a figure which shows Fmax and the tidal deformability of the star itself. And you can kind of see that for different equations of state, they all follow this approximate line. This is what we then refer to as a universal relationship. So this is between Fmax and the tidal deformability. And so we can actually put our own work here as well. So again, this F here is either Fmax, if we talk about the binary neutron star simulations, or the fundamental mode frequency. And we do a max weighted version. So it's MF here. And then all of this as a function of this KT2, which is the tidal deformability. And so the thing to focus on are the different equations of states. So that's where all the different color triangles that you see. So the triangles are the non-rotating ones. I'll show the rotating ones later. Okay, so the black dashed one, so the black dashed line here is the universal relationship for Fmax and this kappa 2. The yellow here, this yellow bit here, is the one for the mass-weighted fundamental frequency and the tidal deformability. So even before you get started, you can kind of see that the two really follow the same, follow the same structure. But this one here is built on theoretical grounds. So this is really more theoretical work, so not simulated work. And so what we're adding here to it is all of these simulations and show that indeed, even in the full kind of simulation setup, in the full dynamical case, the universal relationship holds, and that it's very close to this Fmax universal relationship. So that actually gives us a very nice way of going about to interpret, because as I mentioned before, the Fmax as a function, this Fmax as a function of the tidal deformability, this universal relationship is much less well understood. Why there is this universal relationship, right? Why would the maximum frequency, orbital frequency, somehow be correlated with some intrinsic property of the neutron star itself? Okay, so if you look at the unequal masses, so that those are the squares, this relationship again breaks down. Right? And this is something that we've seen before, that for unequal masses, you kind of get off this nice universal relationship track. Now, first thing that you can do is this simply a coincidence through some dimensional analysis? Right? This is some simple dimensional scaling that you can do, and you can explain the closeness of the simulations in the triangles and the black dashed line. And so what we did is actually calculate in these gray pluses is the approximate contact frequency. Okay, just to give you a sense, a scale of the dimensional of the dimensionality that you're working with. Right, so the contact frequency is, roughly when the two objects physically touch. So that should give you a natural scale, right? Because it's exactly the size of the neutron star, which again is related to the equation of state, and that frequency is plotted here in the process. So you can actually see that those frequencies don't match as well as the precise relationship that we have between the fundamental modes and the Fmax. So it kind of suggests that just purely based on some dimensional argument, you cannot explain necessarily the closeness. So, again, this is not a proof that this relationship is hard, but it gives us another kind of confidence that this is not a pure coincidence based on dimensional arguments. Okay. Now, I should say that the yellow line, so this is the universal relationship between the fundamental mode and the tidal deformability. That is, in a theoretical sense, more understood, and is actually related to the incompressibility of neutron stars. So, irrespective of what equation of state you have, the star is by approximation incompressible, and so you expect the properties to be more or less the same. But now that we've kind of highlighted that the Fmax relationship is closely related to the fundamental frequency, we can now jump ahead and actually postulate that this Fmax property and the universal relationship with the tidal deformability actually just comes from the fundamental frequency of the neutron star. Okay. Now, as I'll talk about a little bit more, but this is not the ironclad proof, but it gives us another hint for the physical interpretation of this maximum frequency of a binary neutron star and the tidal deformability. Why are the two things related? And it's not because of some other physics, but it's simply because neutron stars are incompressible. And because of the incompressibility, the fundamental oscillation frequency is pretty much fixed. And that explains then the Fmax through tidal dynamical tides. Okay, so we can actually, if you now add the rotating sequences here to it as well. So these are the different rotations. So you've got the slower ones in circles and the faster ones in crosses. You can see the universal relationship is really, gets even better. So it gives us also a sense that we know that, the neutron stars are probably rotating by the time they are colliding as well. Okay. Again, this Fmax and the fundamental frequency match is very well. Okay, so one thing that we think this work or this result shows is indeed this concept of the resonance condition being hit. So we have that the Fmax is related to the orbital frequency, but here what we're also looking at is the M2 mode, right, for the isolated neutron stars. And so the expectation is that there is this resonance condition for the orbital frequency and the frequency of oscillation of neutron star. And we think because Fmax and F2F are so close to each other, that this is an exposition that this resonance condition is actually being met. Okay. Now, again, I want to stress that this is not the definitive proof. The definitive proof would be very simple. You do a binary neutron star simulation, but you track the properties of the individual stars, and then hopefully you see the onset of this mode growing as the two objects get closer. But that's at the moment not available in terms of results in the simulations. But we think that this is definitely worthwhile avenue to look into. Okay, so indeed, we wanted to, the conjecture that we have for this work is that there's a strong coupling between the fundamental mode and the tidal fields. That's the starting point. The dynamical tides, will kick in when this tidal forcing frequency, so in this case, this is the orbital frequency, reaches this condition or similarity to this fundamental mode. Okay, so then the 2F mode grows, large amplitude to form a strong tidal coupling near the merger. And the system then satisfies its resonance condition. The energy loss will then be accelerated so that the two objects have very little orbital energy left, and they end up just being forced to collide to each other, which then sets the maximum frequency of a binary neutron star. So that's the conjecture that we are playing with, and that's something that we will want to follow up. So indeed, does this really occur? I guess the only real way to do this is, as I mentioned, you do the full simulation, but you end up also tracking the individual properties of the two stars, and hopefully you can identify the onset of this 2F mode as the resonance condition is being closer and closer.
Excuse me?
Yeah.
So this binary neutron star, this you are computing this Fmax, it's close to merger or it's before merger?
Well,
Red mergers.
okay, so firstly, you have to then define, what do you define to be the merger?
Yeah. So like,
I mean, is it contact? Is that when the merger happens? So when you can kind of see when the two objects, are touching, is that the merger?
I don't know, but I'm thinking maybe the two effects you are looking, say maybe the final of maybe when the two black hole merge, it's just the one neutron star which show the same effect as you are looking in your one star simulation.
Right. So that's why we took the so-called this Fmax, because we expect that this point, when the peak amplitude happens, that the merger hasn't completed yet.
Okay, and
Right.
that's why you have this frequency shifted in the bottom plot.
Yeah, so
Like the maximum frequency is like not at 0, but somewhere later, right?
yeah, so the maximum frequency happens later. So this is when they really collide, and then you get all these, you get the oscillation of the hypermassive neutron star, the bar modes, and all these things that happen afterwards. And so that's why we stay well before that, so that this concept of orbital frequency somehow still works. But this is difficult, right? It's a difficult concept because, to what extent are you sure that even here, that the concept of an orbital frequency still works, right? When there's still enough of two objects that you can consider orbiting each other. And so this is actually one of the things that, as I was mentioning, this was the defense this morning, the student who did this work. One of the questions he was asked, to what extent do you know this is not simply more to do with the hydrodynamics, and that this is really due to the orbital frequency? And that's something that we will have to further investigate. But yeah, what this is, whether this is the right point, we can't for sure tell. But I do think that it does seem like a relatively clean part to work with. Any later than this, yeah, it gets so messy that, I think it would be very hard to still distinguish orbital physics with more the kind of hydrodynamics that goes on inside. Okay, so as I was mentioning, what we hope to do is that we can use these to constrain the equation of state in the future. Okay, so hopefully with future gravitational wave detectors, we can measure both the Fmax, right, the moment when it merges, and also the post-merger signal that comes kind of when there's a semi-stable neutron star, hypermassive neutron star, that then also shows you the oscillation frequency. And if you have those two, then you have, in principle, you have a way to calculate the tidal deformability, right? Because it's EOS independent. So as long as you have these frequencies, you can get the EOS information. So that's one hope. The other one that I mentioned before is, in terms of the effects of mass ratio. So if the mass ratio changes from 1, maybe by measuring the two things, the two frequencies, you can end up inferring the mass ratio. But again, this is purely speculation at this point. More simulation will have to be done to uncover, to see whether there's a clear relationship here. Okay, I just want to take just a few minutes to say some of the ongoing developments that we're doing. I mentioned at the start, we initially started with this conformally flat metric assumption. We're moving on to full general relativity. So this is going from this is the CFC, this is conformally flat formalism, and we want to go to fully constrained, full GR. So no more assumption that the reference metric outside is flat. So that actually, if we fully model the metric, we can also directly extract the gravitational waves, and you don't have to go through the quadrupole approximation. So that's one of the things that we're currently working on, is to push this up. What you see in yellow and green are the two different versions of the code that we were looking at. So most of what I'm presenting is the green stuff, but for historical reference, also the yellow is the initial part of the code. So this is one dimension that we're pushing. On the hydrodynamic side, we're pushing to put in the Maxwell's equations and also resistive hydrodynamics. And we're pushing in this direction by adding neutrino schemes. I can quickly browse through them. So in this case, the ADM. So it really is kind of a trade-off between free evolution, which is BSSN, CCZ4, or kind of fully constrained, depending on whether you put the focus on the constraint equations or on the evolution equations. And so this is the direction we're going to. So this FCF, And all that I can say is that we've been making a lot of progress. We've just completed the first kind of neutron star simulation using this full GR setup. I don't have the results here, but I can show it to you if you're interested. We're also going into this general-relativistic electro-magneto-hydrodynamics. So this conservative formulation that I showed before, we can also extend that for the magnetic field and the electric field. Okay? And so we have to do all sorts of things, but including Ohm's law, so we can add ideal plasma or resistive plasma into this story. How do you do divergenceless handling? So ensure that the B field or the divergence of the B field stays zero. Hyperbolic cleaning to make sure that the Maxwell's equations are stable. And the outcome of this work is some of the results that we're now generating are magnetized neutron stars. So this is actually with, in this case, a toroidal B field. We're doing colloidal beam fields as well. And then we're adding rotation to it, and we're doing non-rotation. And just kind of a brief highlight of some of the simulations that we're doing. I don't have time to show you the results. But again, we're doing it at very high magnetic field, 10 to the 17 Gauss. Okay, finally, also, as I mentioned before, we're also implementing some of the microphysics. So this is some of the, what we call the improved leakage scheme. I'll leave this slide on, which is basically making sure that we model neutrino emission, neutrino transport and absorption and all of these things properly as well. So that hopefully with all of these things combined, we can start doing simulations, not just isolated neutron stars, but also core collapse supernovae in this process as well. So that's pretty much what I have time for today. Yep, that's pretty much what I wanted to say. So I'd be happy to take any more questions that you have, and thank you very much for having me.
Thank you.